continue our discussion about linear classification models. Okay. Last session we talked about methods for obtaining discriminant functions in linear mode, like Fisher discriminant analysis, and today we want to talk about another method for deriving a discriminant model, which is Perceptron algorithm. Okay. In Perceptron algorithm, the model is this, and phi is nonlinear transformation of the features. Okay, so this is a linear combination of nonlinear transformation of data. So we could think of this step as transforming data into another space. We already have seen that in linear regression models, when we had this, we could convert that to this one or this one, and again have linear models with respect to the weights. So so this could be a nonlinear transformation of the input data, and then this is a linear combination of the data. Okay, and what is F? F is defined as it is 1 when A or the input is greater than 0, and it is -1 if its input is less than 0. So in probabilistic models, we know that we encode the output vector as being 0 or 1. Okay, so it could be 0 or 1, but in this case it is more convenient to encode the output vector as 1 or -1. So in Perceptron, the target vector is 1 or -1. Okay, and okay, so this is the output of our model. Okay, and we want to develop an algorithm for deriving W's. Okay, because the variable of the model is the weights. Okay, now what do we want from this model? Okay, we want that if the input feature belongs to the first class, then we need to output of this function to be +1, because when it is +1 means that we infer the output as being in class 1. Okay, so because we encode the target vectors as being +1 or -1. Okay, so if we have x which belongs to class 1, then we want to have this greater than 0. Okay, in this case, if we have this, then the output of this will be 1, and then okay, it is great for us. And also, if an input vector is for class 2, then we want to have it is less than 0 to match to the target vector. Okay, so if we encode the target vector in this way, we could write these two conditions in a more concise way. So in general, we want to have this is greater than 0. Okay, for all of our patterns, for every pattern, if it belongs to class 1, then it is +1, and we want to have this term is greater than 0. Okay, then we want to have, but if we have the data in class 2, then we want to have this less than 0, and the product between this one and this one would be positive, because this is -1 and this is negative, so the multiplication is positive. Okay, so for all patterns we want this condition. So we could define the perceptron cost function as follows. Based on the weights, it is a function of the weights, and it is for all patterns that are misclassified, we calculate this term. So this is the error function. It means that when we have, because these are just for misclassified patterns. So for example, when we have a data that its target vector is 1, but it is less than 0, then it means that it is misclassified. So it is it goes into this term, and then this product will be negative because it is positive and it is negative, or it is positive and this is negative, and so this minus converts it to all positive, because it is a cost function, an error function. Okay, so we want to minimize that. Now for minimizing this cost function, we could use gradient descent method. We will discuss about gradient descent method in deep learning section, but for just quick introduction to that, it says that if you want to minimize function of f, let's say it is we have just in 1D case, if you want to minimize a function, and let's say this is your first and initial point, then you could minimize your function in an iterative manner. The next step that you predict with the gradient descent algorithm is your current step minus and a coefficient times derivative of the function. Okay, So in this case, if we start from here, then the derivative is positive. Okay, the derivative is positive, so when we and this eta is positive, so this multiplication is positive, then when we subtract it from x of t, we will go here. Okay, then we will go there, and in here. In here the derivative is 0, so the x of t plus 1 is equal to x of t, and we get to the minimum. Okay, so we call this gradient descent method, and this could be actually generalized for multiple input dimensions. Okay, so we could write, actually don't worry about that, we will talk about it in much more detail in deep learning session, but for now just it is it is enough to know that it is an iterative process for minimizing function based on the derivative of that function with respect to its inputs. So we could do the same thing with the parameters of our cost function, and using gradient descent you could obtain that it is the gradient for parameters w, so it is equal to, and we call this coefficient learning rate. You could actually set that in real problems. You could it is a constant that you could set. Okay, so we update the weights in this manner. Okay, as you could see, our update term is phi n t n. So, and this is for just misclassified patterns. Okay, and so this is just for misclassified patterns. Okay, the great thing about Perceptron algorithm is that we have a theorem for Perceptron algorithm. It is Perceptron convergence theorem. It states that if there is an exact solution, so Perceptron convergence theorem states that if there is an exact solution, means that if your data is linearly separable, okay, in this case they are linearly separable, but because we know that there is a solution. In this case the solution is not unique, as you could see, all of these are solution of these problems. Okay, and if there is an exact solution, then the Perceptron algorithm could reach that solution in finite steps. Okay, so it is great about Perceptron algorithm that we know that it could reach the exact solution. But the problem is, in real world applications, sometimes the convergence is too slow. And also we know that if they are not linearly separable, then the algorithm fails and will never converge. If we have an outlier, something like this, from this class, or maybe something like this, then the Perceptron algorithm will never converge, and this is so bad about that. And also we cannot interpret the output as probabilistic outputs. Okay, we sometimes we want to interpret the output of an algorithm based on the probabilities, and say that, okay, the output of the algorithm is 70%, means that the input data belongs to the class 1 with 70% confidence. Okay, so we like to have probabilistic output, but in Perceptron we don't have such a thing. Okay, so now this was Perceptron algorithm, but now we want to talk about probabilistic discriminative models. As I mentioned, it is very common that we like to have probabilistic outputs. Okay, so we want to have probabilistic discriminative models. Okay. We have very different models in probabilistic discriminative models. One of the most important one that we want to talk about, that is logistic regression, that you probably heard its name. Actually, logistic regression is a model for classification, so you should not confuse that with regression models. It's called logistic regression, but it is a model for classification, but not the regression. Okay. In logistic regression, so let's say we have two classes, C1 and C2. This is in two classes case. Okay, we want to obtain the probability of class 1 based on our input features. As I told you before, when we have X, then we could convert it with a transformation phi, and then apply our models on phi directly. Okay, so I just show that with phi. Okay, and we work in phi space rather than the input feature space directly. Okay, so we want to estimate that. Okay, in logistic regression, we estimate that with a non-linear function. It's called logistic sigmoid of linear combination of the phi features. Okay, and the logistic sigmoid is defined as 1/1 plus and sigmoid means that S-shaped. If we plot the sigmoid of X, then we will see it is something like this. Okay, so as you could see, it maps all the real axis into a finite interval between 0 and 1. Okay, so it somehow converts this into a probabilistic output, because the output is always between 0 and 1. Okay, so in other words, we want to, because we have two classes, then it seems that it wants to approximate the Bernoulli distribution parameter. So if, let's say, our data set is something like this, so again, I mentioned that phi of n means that we transformed our input features with phi and store phi and tn. Okay, so it is our data set. Then we can write the likelihood function as, because the samples are IID, so we could write them as so this is Bernoulli distribution. If you remember that this is Bernoulli distribution, it was x p1 minus x 1 minus p. Okay, as you could see, this is Bernoulli distribution, and y of n is the probability of class 1 given phi. Okay, so if we write the maximum likelihood term, maximum log likelihood, we could actually, instead of maximizing log likelihood, we could minimize the negative log likelihood. So we could define the loss function as minus log of likelihood function. So that is sum over Tn log Yn plus 1 minus Tn so this is the loss function in logistic regression, and the name of this cost function, you probably will hear about this a lot. Its name is Cross-Entropy Loss. Okay, so it tells you if you have a Bernoulli distribution of your two classes data and you use maximum likelihood, then you obtain cross-entropy loss. And the great thing about this cost function is that it is convex. We didn't talk about convexity so much, but just to mention that optimizing convex function typically is very easy. So it is great to have convex function. Convex function means that we have bowl-shaped function that they have unique and global minimum. Okay, so if we have something like this, this is not convex because we have some local optimum which are not global optima. Okay, now we could write we could apply gradient descent to update the weights. Okay, if we calculate the gradient, it is equal to sum over theta yn minus tn phi n. So it makes sense. Maybe it is a little maybe it seems a little complicated at first, but when you derive the update factor for the weight, it completely makes sense. It tells you if you want to update weights, the update is given by the difference between the output of your model and the actual output times the input features. So if we have perfect output for the input, we don't have to update weights, okay? And the output is proportional to the difference between the target values and the output of the model. For multi-class, so as you could see in here, we model the probability of class 1 with sigmoid, logistic sigmoid of W transpose phi. So we could actually generalize that for multi-class problem. For multi-class problem, we could model the class K, probability of class K given phi with exponential function of AK, AJ, in which A of K is the linear combination of input features. Okay, so in this case we have kind of normalization on our outputs. You could see this as you have some output. If you have n class, then you have 1 to n output. Then for estimating that, you just need to calculate, and let's say these are input features, phi 1 to phi m maybe. Then for the first class, these are W1 to WM1 and so on. So if you are familiar with neural network, you could see a similarity between these and neural networks, but if you don't, just don't worry about them. So just in here, as you could see, I just want to visualize this for you. So this means that it is A1. Okay, A1 means that W11 times phi 1 plus W12 times phi 2 and so on. So, and then for converting this output into probabilities, one way is to using this. So if we use this, then the sum over all of the outputs, because when we convert them to probabilities, then we want to have sum of 1. So the sum of all these C1 is 1, and each of them is between 0 and 1. Okay, so we could interpret them as output probability of class K. Okay, and we actually call this softmax. We also talked about this in deep learning section, but for now, just remember that we call this softmax function. Okay, so similarly, if you apply maximum log likelihood, it means that the cost function is sum over all data, sum over all classes, T of nk means that this is the output of nth data and class K, because the data, the specific data has n different elements, and each of them correspond to the output values for each class. Okay, so this is the probability of class 1, class 2, and so on. So we have t n k and log of output y n k. Okay, so this is very similar to 2D case. You could see that for 2D case you could write this as for 2 class case. Okay, it is very similar to that. So this is cross-entropy loss for multi-class. Okay, and in this case also, if you want to update the weights of output j, because in this case you have j output, so in this case it is equal to some overall data, and again it is proportional to difference of prediction of model output and the actual output of that target times input features. Okay, so this is logistic regression. So now you know about logistic regression. Now we want to see how to use them in Python with scalar. Okay, let's do this. Okay, for using Fisher discriminant analysis and Perceptron algorithm and logistic regression is scalar, the scikit-learn has all of them in itself. So if you search for linear discriminant analysis, you could see a short explanation about how does they work, that we talked about them. And LDA means linear discriminant analysis, which is Fisher's discriminant analysis. Sometimes it's called LDA. So as you could see in here, for using that you just need to use linear discriminant analysis from discriminant analysis. You could import that from scikit-learn and then initialize your classifier, then fit that on your data. So after that you could use your data with predict method. Okay, that's it. So using linear discriminant analysis is pretty straightforward. Now for using Perceptron algorithm, also you could define Perceptron in here, and from linear models, because it is a linear model, you just import that from linear models, then initialize your classifier. The tol is tolerance, means that when you want to the algorithm stops, because if you want to have perfect output classification, if the data is not linearly separable, then the algorithm is not converge. So if you want to have some kind of tolerance to just not to have perfect output, but some tolerance to allow your model to have some error, then you could use tolerance. Okay, and also there are some other parameters like alpha. Actually you could read that from here. it is the regularization term. Perceptron in scikit-learn is implemented with regularization term. So you could set a regularization factor for that, okay? And the regularization is L2 regularization, okay? So your weights have, so your cost function of Perceptron has another term which is L2 norm of the weights, and this is the lambda that we talked about that, okay? And other options that you want, maybe you want to set, like maximum iterations, okay, which is because it uses iterative methods to update weights. How much do you want to update your weights in maximum state? Okay, and after that you could get a score of your classifier with score method, okay? So using Perceptron algorithm is also easy, okay? And as you could see in here, you could also, instead of L2, you could use L1 or ElasticNet. We have not talked about ElasticNet, but for now, you could use none or L2 or L1 for regularization, okay? Okay. And for logistic regression, also you could import that from linear models. Then it is a sample from Iris dataset. So because it is a multi-class problem, you should in multi-class you should write multinomial, and then you could fit your model on your training data and then get the probability of your inputs. And in logistic regression, we have also, you could also have regularization, okay? The penalty could be L1 or L2. One of the terms in the cost functions that included by default in scikit-learn is regularization. So when we talked about logistic regression, we don't talk about regularization, but when you want to implement that in scikit-learn, you could always keep in mind that you could add regularization factor to that. In here, the regularization factor is C, but you should just note that the C is inverse of regularization strength. So if you use larger value of C, it means that you want to have lower values for regularization. So it is inverse of lambda, okay? Okay, that's it. So you can now use Fisher discriminant or LDA or Perceptron algorithm or logistic regression for your data to classify them, okay? Hope to see you in the next sessions. In the next sessions, we talk about other models for classifications, and yeah, that's it. Hope to see you in the next session. Bye.